Okay, can you see the screen? Hello everyone, can you see the
Yes,
screen?
yes, yes, ma'am.
Okay, fine. So let's not wait much now. Let us start our experiment number one, that is sampling and aliasing effect. Actually, today we are going to study only sampling because aliasing will be covered in the next experiment also. So we'll see aliasing also a little bit today and little bit in the next experiment. So let us start. What is sampling? Does anyone know? Can you tell me the simple English meaning of sampling? What do you mean by sampling? If you want to do samples, means what? Anyone? What do you mean by sampling? Prototype of my any project, prototype of product. No, I don't know why you are saying prototype. Okay, anyways, let me tell you, sampling means there are so many things, let's say so many people in the college or so many people in the TC3 class. Let's say we are taking the example of TC3 class. But if I want to know that how the TC3 class is, how the students of TC3 class is, so what I will do is I'll pick random students, I'll pick some random students from the TC3 and I'll evaluate their characteristics. Then I will come to know the overall characteristics of TC3. So sampling is the same thing. Sampling means we are taking some of the examples or some of the points by which we can get the information about the whole thing. Out of whole thing, I'm taking only some points, some examples, some samples. But by studying those samples, I can uh, be aware about the whole thing, right? So that is known as sampling, and the same thing we are going to do over here also. See, first of all, before starting it, let me tell you that why sampling is important. Because see, whenever we are sending the continuous signal, let's say sine wave signal, I'm taking a very easy example of sine wave signal. If I want to send a sine wave signal from one place to another place, then it is very easy to say sine wave signal, but it is very difficult to take the value at each point of time in the sine wave signal, because sine wave is the continuous wave where at each point of time you will get different value. It means, in other words, you can say that there are infinite number of values in the one sine wave signal. So if you are sending a one sine wave signal, it means you are sending infinite number of values by using the transmission medium. So if you don't want to send that infinite number of values, then you can take some of the samples of that sine wave signal and then you can send that. And at the receiver side, by combining those all samples, you can again recover your original signal. That is all about sampling, right? So ultimately what we are doing in the sampling, we are converting our continuous time signal into the discrete time signal. Sampling equal to conversion of continuous time signal into discrete time signal. That is the definition actually. So see, first definition is given: the process of measuring the instantaneous values of continuous time signal in a discrete form. It means, I have taken very easy example of sine wave, but let's say your continuous time signal is something like this, very random, right? So whenever you will send this type of signal, it will be having infinite number of values. So what you are doing is, you are taking some of the points from this signal, and those points are nothing but the spikes, right? This spikes. Okay, so these are the samples of this signal. And at the receiver side, what we are going to do is that we will see how the process will be happen at the receiver side, right? So in today's experiment, we will see that at transmitter side how this signal will be converted into this, and at the receiver side how this signal will be again converted into this. That thing we are going to see today in this experiment. Okay, so whenever you are taking some of the samples of this signal like this process is known as sampling process. Any doubt, anyone? Definition: sampling. I hope it is clear, right? It is very easy definition that if you are converting, yeah, if you are converting continuous time signal into discrete time signal, that is known as sampling process. Okay. Next is, before going to next point, let me take one example into the multisim. So I will explain you the sampling period TS and sampling frequency FS by taking one example in multisim. So let me open the multisim in that case. So how you need to do the sampling? That is all about sampling period and sampling frequency. Very, very important parameter while doing sampling. That what should be your sampling period while converting continuous signal into discrete, or what should be the sampling frequency. Actually, that is given by one theorem also, that is known as sampling theorem or Nyquist rate, that we will study in upcoming slides. But let me show you one very important thing or very important component in multisim, which will do a task for different type of signal differently. For example, can anyone say if I will add two DC signal, one is of 3 volt and one is of 5 volt, what will happen if I will add two DC value, 3 volt and 5 volt? So what will be the answer? One signal is of 3 volt DC, second signal is 5 volt DC. So what will be the addition of these two? Very simple. Hello? Anyone? What will be the addition of 3 volt plus 5 volt? Simple, simple question. It's the addition only. 8 volt, right? Okay. If I will do multiplication of both, then what will happen? 3 volt into 5 volt. If I will multiply these two signals, then obviously I will get 15. Okay, now my question is not only for DC. Now I am saying that if I am having one DC signal of 3 volt and one AC signal of 5 volt, then what will happen? What will be the output of multiplication? I repeat, in multiplier, if I will apply one 3 volt DC and one 5 volt AC, then what will be the output? So maximum possible cases I have is both the signals in the multiplier are DC. Let's say both the signals are DC, then you are saying that you will simply get 15 volt. If one signal is DC and second signal is AC, then what will happen? And third possibility is if both the signals are AC, then what will happen? So that we are going to see first into the multisim, and then I will say that how the sampling will be done into the multisim or in the real life even. Right, so let me take first of all multiplier block. So see, from sources control function blocks is there in which one multiplier is there. So you have to take that multiplier from there, and now I will apply different type of input signals. For example, first of all I am applying both DC batteries to X and Y. And I will require one ground also, because the battery, negative of the battery will be connected to ground. Let me close it. So I am applying V1 to X, right, and V2 to Y. And the negative of the battery will be connected to ground. Right. Now, if I will apply oscilloscope at the output side, you can apply multimeter also because both are DC. But next example I am going to take as AC. That's why I am using oscilloscope. Okay. Now, if you will run this circuit and both the voltages are 12 12, so let me make it small because multiplication, otherwise multiplication will be very big, right? 12 into 12 will become 144. I don't want that big voltage. So let's say 2 into 3. I will run this circuit, I will get the output some DC voltage because both inputs are DC, so obviously output will be DC. But how much voltage you are getting, that let's see. Channel A is 5 volt per division, and here one division and 1 volt is being covered. It means 6 volt, right? And 3 into 2 is 6. So you are getting 6 volt. As you are saying that the voltages will be simply multiplied, and that's what we are getting at the output side. Now my question is, if you are removing, let's say, one of the DC volt and you are applying AC voltage over there, AC voltage, right? So let's take AC voltage from the sources again, close this, connect this voltage to Y. Now again my question is same, what will be the answer? If let's say I am applying 2 volt peak voltage over here, so this is 2 volt sine wave signal of 1 kilohertz frequency, and this is 3 volt DC signal of 0 hertz frequency. So what will be the answer? What oscilloscope will display? Do you want to guess what will happen? 2 volt sine wave, 1 kilohertz frequency, 3 volt DC, 0 hertz frequency. If I will multiply these two signals, what will be the output of oscilloscope? We will see both. You are asking me the question. I won't answer. Arafat. Yeah, you guess that we will see AC and DC both. Okay. Anyone else wants to guess what will be the answer? Be interactive, everyone. Are you present or are you just starting the lecture and you are doing your work? I don't want that type of students, huh? I hope everyone is listening. So give me the answer. Both AC and DC. Okay, so in multiplication, Tebot was saying that both AC and DC will be displayed into the CRO. Okay, Shekhar. Shekhar.
Yes, ma'am. Yes,
Yeah.
ma'am.
What is your guess? What
I think AC and DC is AC, ma'am.
AC? Only AC.
Only
Okay.
AC. Yeah.
Okay. So Shekhar is saying that only AC will be displayed. Krishna is saying only AC will be displayed. Okay. Okay. So if you are saying only AC, then how much voltage will be there at the output? 2 volt is AC voltage, 3 volt is DC voltage. If you are saying only AC voltage will be there, then what will be the voltage? 2 or 3 or 5 or 6 or what? Huh? Krishna and Shekhar. What will be the voltage level of the AC voltage? Okay. So, okay, Shekhar is saying that 6. Okay, fine. So both the voltage value will be multiplied. Yeah, Krishna is saying, let's see. Okay, fine. See, both the value of the voltages will be multiplied, but whenever AC and DC both will be multiplied, let me tell you what will happen. You can simply do simple multiplication. See, I am doing a simple multiplication over here. Let's say this is my sine wave of 2 voltage. See how multiplier is working. Simple multiplication it is doing. And this is 3 volt DC. See, if I will multiply 3 with 0, what will be the answer, everyone? 0, right? 3 multiplied by 0 means 0. If I will take, let's say, this peak value is 2, right? So 2 multiplied by 3, what will happen? 6. I'm taking some of the points only. So 6 volt. Again, I will multiply, let's say, 0 with 3. So what will happen? Again, I will get 0. If I will multiply minus 2, this is minus 2, right? Minus 2 with plus 3, what will happen? Minus 6. So minus 6 will be somewhere here. Again, if I multiply 0 with the 3, I will get 0. And if I will multiply the remaining points with the 3, obviously I will get in between these 2 points. So I will get this type of sine wave signal only which is having the peak value 6 and minus 6, everyone. Right? So Shekhar is right. Right? So what you are doing multiplication of values, not the signal. Right? So at every point of time, the values of the signal and values of DC will be multiplied, and you will get this type of signal. Let me decrease the frequency. See, now let us see how much voltage is there. So see, 5 volt per division. So one division is covered positively and some more, 1 plus something, right? So 6 volt in the positive cycle and 6 volt in the negative cycle. Simple, right? So you are getting 6 volt peak signal in the sine wave and 12 volt peak to peak. 6 volt peak signal and 12 volt peak to peak signal in the sine wave in the output. Is it clear, everyone, how multiplication is being happen? Right, I have already seen some of the points multiplication. Is it okay? AC into DC. Okay, now my question is, if I am multiplying AC into DC, then I am getting AC. But if I will add AC plus DC, then what will happen? Yeah, Krishna, Shekhar is right. Shekhar is understanding today. At least today he is getting what is going on. Okay. So anyone, can you say if I am adding these two voltages, AC plus DC, then what will happen? Multiplication we have seen. Now addition will give you what? Hello everyone. 5 volt DC. Okay. Now you do addition over here. Simple. 0 plus 3. It means your signal will be started from 3. See, we have already seen that whenever you are adding DC signal to the AC, your signal will be shifted to that DC voltage. For example, DC voltage is 3, then your signal will be shifted to 3 from 0. Right? So you will get signal like this. You can try by yourself. You will get this type of signal. Your signal will be shifted up because you are adding 3 volt to every point of AC signal. This is minus 2. Let's say minimum value of this sine signal is minus 2. If you will add 3 plus minus 2, then you will get 1. So minimum value you will get is 1. Right? This is 1. You will not get even 0 if you are taking this type of value. So whenever you are adding DC plus AC, your AC signal will be shifted to the value of DC voltage, and when you are multiplying DC into AC, you will get AC only, but the value of amplitude will be multiplied. Is it okay, everyone? You must know this. Okay. Next is, if I am applying both AC, then what will happen? Let's say I'm copying this voltage or signal and I'm putting it to here. Let's connect it to X, and you can change the value also. Let's say from 2 volt I'm making it to 4. Okay, now I am applying 2 volt into 4 volt. I'm applying same frequency. You can keep different frequency also, but if it is of same frequency, what will be the output? Both are AC, then what will be the output, everyone? I want answer. Both AC, then what will be the output? It will be multiplied by 4. Okay, so it means, Arafat, you want to say that 2 into 4, 8 volt signal, AC signal you will get at the output, right? Okay, fine. So let us see what is happening. So, okay, so you want to say this. Let me erase this first of all. So you want to say this, that you will get this type of sine signal only at the output, and this will be 8 and this will be minus 8, right? Am I right, Arafat? You want to say this only? Okay. Anyone else wants to say something? Okay. So now let me tell you, before showing it into the CRO, let me tell you what will happen. Let's say this is 2 volt signal. This is 4 volt signal. If I will multiply both the signal, you just have to do multiplication, guys. 0 into 0, what will happen? 0. Okay. 2 into 4, what will happen? 8. So let's say you are getting 1.8 over here. Again 0 into 0. I am taking some of the points only. So you will get 0. Now this is minus 2. This is minus 4. Can anyone say what is the multiplication? Minus 2 into minus 4? Anyone? Minus 2 into minus 4 means
Eight.
plus 8. Yes, plus 8. So it means whenever you will do multiplication of these 2 points, you will not get minus 8. You will get plus 8. It means your point will be at here only. Again, if you will multiply any minus number, see, minus number into minus number, you will get always positive. So your signal will be something like this, guys. It means you will not get negative cycle. Your whole signal will be shifted to positive. Let's see, is it happening into the oscilloscope or not? So let me open the oscilloscope. See, you are not getting negative cycle, right? You are getting 8 volt, no problem. See, you have applied 2 volt peak, 4 volt peak. So 2 into 4, 8 volt. 8 volt peak you will get, but minus 8 volt you will not get. At that time also you will get 8, right? Because minus 2 into minus 4 will become again 8. So 8 volt peak signal you will get. Is it clear, everyone? It will be clipped with a negative. Yeah, not, yeah, no, it is not clipping the negative, but multiplication property is saying that minus into minus will be plus, right? That's why it is happening, that your whole signal will be shifted up. You will not get any negative value when you will multiply two sine waves or two AC waves. Yeah. Okay, so can I move forward now? Is it clear? Now I am going towards the sampling, how sampling is done. Okay, so let me tell you that how sampling will be done. Now what I want to do, if I want to multiply sine wave with some signal so that I can get a sampling. Sampling means I will get some of the samples like this, right? So sine wave is simply converted into some of the spikes. So I'm taking only some of the samples of the waveform. So if I want to do this type of thing, this is the input, this is the output. So what should be the multiplication signal? How the multiplication signal should be? So let me tell you, if I will apply, let's say, this type of pulse train or spike signals, all are positive, and I have to apply it positive. If I will apply negative, then what will happen? Negative will become positive. I will not never get this negative cycle. I want this negative cycle also. So I will apply only positive spikes. And let me tell you what will happen. See, I need to do the sampling in such a way so that this values will follow the amplitude of sine wave signal, envelope of the sine wave signal. It means what should be the value of this spike? What should be the value of the spike so that this will be multiplied with sine wave? Then the answer will be sine wave. What should be the value of spikes? Everyone. Can anyone say? I repeat. I want this into this should be this. It means it is the amplitude of sine only, right? So whatever value of sine wave is, the same value I am getting the spike value. So what should be the value of these all spikes? Anyone? Anyone? It should be 1, right? 1 into anything is anything. 1 into sine wave, it means sine wave, isn't it, everyone? So I will try to keep this pulse wave in such a way so that the value of this pulse will be 1. So now see what will happen. This 1 will be multiplied with this value. So you will get this value at the output side. If this spike will be multiplied with this value, then you will get this value at the output side. Same way for all the values. If this will be multiplied with this value, you will get this spike, and so on. Okay, so 1 multiply by this, 1 multiply by this, 1 multiply by this. So I want to do the multiplication of sine wave, that is AC signal, with this type of pulse train. And this type of pulse train is available in the multisim. Let me tell you where. So if you will go to again the signal voltage sources, then pulse voltage is there. Pulse voltage. If you will take that pulse voltage as the another input of multiplier, then let's see what will happen. Now let me open this property of sampled or pulse voltage. So see, in pulse voltage they are saying that initial value is -1 and pulsed value is 1. What I want exactly, initial value is 0 and pulse value is 1. So I have to set this initial value 0 and pulse value 1. So let me set it, initial value 0 and pulse value 1. Okay. Second, here they are saying that pulse width is zero point 0.5 millisecond. Pulse width means what? This is the pulse. Actually the pulse width can be any value. If you want it bigger, then you can keep it this much. Let's say this is zero point 0.5 millisecond, but I don't want this much pulse width. I want a single spike. It means my pulse width should be as minimum as possible. I cannot keep it 0, but yes, it should be very minimum in microsecond or in nanosecond. So let me set this pulse width as very small, 0.001 microsecond. Let's say it is very small, right? Everyone, are you able to understand what I am setting? Initial value 0, pulse value 1, and pulse width should be as minimum as I can. I can keep it 1 nanosecond also, no problem. So I have kept almost the same thing, 0.0001 microsecond, or I can simply put 1 nanosecond. Both are same, right? So 1 nanosecond pulse width. Now period means what? That how many samples you want to do for one cycle. You want to do, see right now I, how many samples I have done? 1 2 3 4 5 6 7 8 9 10. 10 samples in one cycle. So if I want to divide this signal into 10 parts, then what should be the frequency or what should be the time period between two samples? So these are the two pulses. So what should be the time in between these two samples? What is this time? That is known as sampling period, everyone. This is known as sampling period. I will take different value and I will tell you that what this period will give effect on the sampling. So let me set right now. It is, let's say, 0.05 microsecond. I will increase and decrease afterwards. Right now I am setting it 0.05 microsecond, and let's see what is happening at the output side. So whenever you will run this circuit and see the output, let me increase or decrease what is happening. Okay. See, I am getting this type of spikes. Now, let me change. Now you will think that how I will change this period. So I will tell you how you can change this. Don't worry. Wait for some time. Now, if I will change this period to, let's say, zero point 0.5 microsecond. And now if I will run the circuit, then what will happen? Again, I am getting a spike. See, I'm getting this type of, it is sine wave only. See, but so many samples are there. If you will increase the frequency, decrease the frequency, then you can see the samples. See, in one sine wave, I have put it so many samples, right? Now, if I want to put a sample value very small, I don't want to put this many samples. So let's say, what is, it depends on the frequency of your signal. What is the frequency of your signal? 1 kilohertz, right? So if your frequency is 1 kilohertz, then what is the time period of this 2 volt sine wave? 1 upon 1 kilohertz, that is 1 millisecond. It means one cycle is of 1 millisecond. If you want to do only 10 samples for 1 millisecond, it means you have to divide your 1 millisecond divide by 10. 1 millisecond divide by 10 means what? Can anyone say 1 millisecond divide by 10? Zero point 0.1 millisecond, so zero point 0.1 millisecond. And let's see, you will get only 10 samples. See, only 10 samples, 5 samples for positive cycle, 5 samples for negative cycle. You are looking at only 4 samples because 1 is the zero, the zeros are in between, right? So total 10 samples are there per cycle. So you are reducing the number of samples. So how many samples do you want in one cycle? For that you have to set this sampling period. Now, do you understand what is sampling period? I was telling you that I will let you know that what is the sampling period and how it will affect your samples, right? So whatever, let's say now, instead of zero point 0.1 millivolt, if I want to make 20 samples, right? If I want to make 20 samples, then I have to do 0.05 millisecond. Then I will get 20 samples in the signal. Let us see. See, 10 samples in the positive cycle, 10 samples in the negative cycle. So, what amount of samples you want in one cycle, depending on that, you have to set your sampling period. Now, you will think that how we will come to know that we should take 10 samples or 20 samples or 50 samples, or how many samples we should take while doing the transmission, right, everyone? You will think that how many samples we should keep while doing transmission. So let me tell you, to decide that how many samples you should take for doing the transmission, that is given by Nyquist rate. And why Nyquist rate is given? Because let's say, if you are doing sampling in such a way so that you are keeping, let's say, zero point 0.5 millisecond, and you are getting only very less samples, zero point 0.2 millisecond, and you will get only 4 samples. So at the receiver side, can anyone get the original signal from this type of sample? That is either sine wave or which type of triangular wave. If you will join these all samples, then you can get triangular wave also, right? So at the receiver side, the original signal cannot be reconstructed if number of samples are very less, right? If number of samples are very less for one cycle, then at the receiver side, reconstruction is not possible. So, to do a proper reconstruction at the receiver side, one sampling theorem or Nyquist rate is given, and according to that Nyquist rate only, we have to keep the sampling period. Now, let's go to the PPT again. To discretize the signals, the gap between the samples should be fixed, and that gap can be termed as a sampling period. I have already explained this, right? What is sampling period? And sampling frequency means 1 upon Ts, right? So 1 upon sampling period is sampling frequency. Now the question is how this sampling frequency we should keep. And for that, the next, before going to the Nyquist rate or sampling theorem, let us see one video, very important video, right? In that video they have explained that how much your sampling frequency should be. But before watching this video, anyone is having any doubt in sampling period? Everyone, how we have set this setup to do the sampling? Any doubt, anyone? Can I move forward? Okay, okay, Gloria. Okay, so everyone understood what is happening. Okay, fine. So let us see that video first now. Shekhar, I will explain it after watching this video. Just wait.
Grammarly does more than catch errors.
Now, my question
With
is, are
Grammarly,
you
you
able
can
to
find really
listen
good,
the audio,
no,
everyone?
perfect words that make your writing sharp or
Are you
explicit.
able to listen the audio? Okay, fine. So let's see.
Sampling theorem. In this lesson, the learner will be able to define sampling, explain sampling theorem, demonstrate the encoding of digital data into digital
Ma'am,
signal.
Yes.
Before
display
learning
visible
about
name.
sampling theorem,
Yes.
Display is not visible.
Screen is not visible. Just a minute. Maybe.
the learner will be
Now
able
is it
to
visible?
define sampling,
Yes, ma'am.
Yes.
Yes.
Okay, fine.
explain sampling theorem, demonstrate the encoding of digital data into digital signal. Before learning about sampling theorem, let us first learn what is meant by sampling. Sampling means taking a sample or samples from a population which gives the entire detail about the whole population. To be more precise, taking a sample of food gives us the taste of whole food. In data communication, sampling means taking sample of signal at equal intervals which gives the entire data about the sampled signal during reconstruction. Now, let's see an application of sampling, encoding, decoding in data transmission. Consider a person sends a voice message to another person. The voice of the person is an analog signal. This analog signal is sampled at regular time interval so that it can be reconstructed to original analog signal. The digital data is encoded for security purpose and to avoid loss of data while transmission. At receiver side, the encoded signal is decoded back to the digital data. From the sampled digital data, the original audio file is reconstructed and the receiver hears the voice message. From this, we learn that sampling is used to convert the analog signal into digital signal, and we also learn that encoding and decoding plays an important role in data communication. Now, let us learn about sampling theorem in detail. Sampling theorem. A band limited signal can be reconstructed exactly if it is sampled at a rate at least twice the maximum frequency component in it. The maximum frequency component of G of T is Fm.
Okay. Just a minute.
Hey guys.
operating system.
Yeah,
Do you want to say
I
something?
want to say
Or Dalo?
oh, I'm really tired. Please, Teddy, don't write such things.
No, ma'am. I cannot hear you.
Hello, Samad.
نعم زمبرستي.
منو
ये तो नहीं होगी
eh እኔ
कहाँ
እኮ አሁን እንትን ስል
ये
ሁሉም ጸጥ ብሏል። ለማረጋጋት እኮ ነው።
جماعة
እም
انت بيت ريتشن.
አንተ ሰው አለ እኮ እዚህ ምን ሆነህ ነው እንደዚህ የምታወራው? አጸያፊ ነገር ጥሩ አይደለም እውነት።
David.
Hello, can you hear me now?
David, someone.
yes ma'am
Okay, fine. So I don't know why, but there is some audio problem. I'm not able to speak anything from here. Okay, fine. So let me tell you what was in that video. In that video, they were saying that in sampling theorem, what you are actually doing one step to convert analog to digital. See, digital is nothing like digital is present in the real life, right? Everything is analog. But whenever we are doing transmission, we prefer digital rather than analog because there are so many advantages of digital over analog. So we want to convert our analog signal into digital, but we cannot convert it directly. The first step is doing sampling, and that's why we are studying this as an experiment one. In experiment one, we are doing actually first step of converting analog signal into digital. In next experiment, second experiment, we will convert it into digital. Then we will see that after sampling, what is the process that converts the signal into digital. Okay, so this is the first step to convert analog into digital. And next they were saying in the video is, if you are taking an example that whatever you are speaking, let's say I am speaking through the microphone, right? So whatever I am speaking is analog signal, right? But you are again listening that analog signal very well, but what is the process, what is the inside process is going on, that my analog signal is first being sampled, and then that sampling process, after sampling process, that signal will be converted into digital. And to do that, there is one process named as quantization that we will see in the next experiment, right? So that signal will be converted into digital, and then see, I am doing communication with the computer, and computer works on the binary. It means my data will be encoded into the binary form, and then it will be transmitted to your computer, right, through the internet or through any media, right? So you are getting digital data, your computer is getting digital data. But don't worry, I'm not right now, I'm not showing any PPT, I'm only speaking, Shekhar. Okay, so what you are getting in your computer is you are getting a digital encoded data. So you will decode, your computer will decode that data, and you will again listen. Whenever you will listen, your digital data will be again converted into analog, and you will be able to hear it. Okay, so your digital data will be converted into analog in your computer. And whatever I am speaking here, from here, the analog signal will be converted into digital. Okay, so that's what they have explained. And in the last point, they have explained the sampling theorem, that how much your sampling frequency or sampling period should be, so that at the receiver side you can reconstruct your original signal. For that, your sampling frequency must be greater than or equal to twice of maximum frequency. So what is maximum frequency here? Let's say you are applying 2 hertz, sorry, 1 kilohertz. Just a minute, let me show you. Let's say you are applying 1 kilohertz sine wave. So what should be this frequency? This frequency must be greater than or equal to 2 kilohertz, right? This is the minimum frequency you should have, that is 2 kilohertz. You can keep it 3 kilohertz, but you should not keep it less than 2 kilohertz. So 2 kilohertz is the minimum frequency you have to keep here, so that you can get reconstruction, proper reconstruction at the receiver side. That is known as sampling theorem or Nyquist rate. Now let me show you that in the next slide. See, they are saying that suppose that a signal is band limited with no frequency components higher than W hertz. So W is the maximum frequency. And why I am using this word maximum frequency, because as I already told you this in the first chapter, in the theory chapter, that whenever we are transmitting signal, we are not transmitting only one sine wave. Right, we are transmitting multiple signals of different frequency, different amplitude, different phase, and that is known as composite signal. And whenever you are transmitting composite signal, then your composite signal are having multiple frequencies. So which frequency you have to take for sampling theorem or Nyquist rate? Maximum frequency. For example, in your composite signal, one signal is having the frequency 1 kilohertz, second frequency is 500 hertz, third frequency is, let's say, 1.5 kilohertz. So what is the maximum frequency out of this three? 1.5 kilohertz. So this W is 1.5 kilohertz. Even if you are transmitting three signals together, you have to consider maximum frequency while calculating the Nyquist rate. So your sampling frequency must be greater than or equal to 2 into 1.5, that is 3 kilohertz. Okay, this is something about Nyquist rate, and this is also known as sampling theorem. Any doubt, anyone? Nyquist rate. This question can be asked in one mark. What is Nyquist rate or what
Ma'am,
is sampling theorem? Yes, Arafat.
in the last line it says something about the twice the frequency.
Yeah.
Like if you are sending any like sampling rate will be twice of the signal you are sending.
Yes. Twice of the frequency what you are sending. So if you are sending only one sine wave of 1 kilohertz, it means your sampling frequency must be at least minimum it should be 2 kilohertz. Okay, you can keep it 3, 4, 5, but you cannot keep less than 2. Otherwise, what will happen at the receiver side? Your original signal cannot be reconstructed again. Right? They have taken so many examples and they have put at this conclusion that whenever they have tried on the different data, if they have put at the less frequency, less sampling frequency, then they are not able to reconstruct at the receiver side, and that is also known as undersampling. Right? If you are keeping the frequency less than 2 of W, then it is known as undersampling. Okay, and if you are keeping your sampling frequency equal to 2 of W, then it is known as proper sampling. And if you are keeping it greater than 2 of W, then it is known as oversampling. And why oversampling word is used? Because there are some disadvantages also if you are keeping it twice of W. And what is the disadvantage? Let me tell you. If you are keeping, let's say this is your 1 kilohertz frequency, right? So if you will put it greater than 2 kilohertz, let's say 10 kilohertz. So 10 kilohertz means what will be the time period? 1 upon 10 kilohertz. What is 1 upon 10? 1 upon 10 kilohertz. 0.1 millisecond, right? Everyone. if I am putting 1 kilohertz as my input frequency, then sampling frequency must be at least 2 kilohertz. But if I am putting it over sampling, then it means I am putting it 10 kilohertz. So it means it is 0.1 millisecond. So if I will put it 0.1 millisecond, then I will get 10 samples in one cycle. Why this is known as oversampling? Because you still require to send 10 values while doing transmission. So again, see, your bandwidth is limited. Why you are converting analog into digital? Because your bandwidth is limited. You cannot send infinite number of values of the sine wave. So you want to decrease these values. If you want to decrease this value, you cannot, let's say again, put the oversampling, because oversampling means again you are increasing the number of values, right? So even if you are doing, let's say, greater than 10 kilohertz, let's say you are putting it point, instead of 0.1 millisecond, let's say you are putting zero point 0.5 millisecond. Sorry. It is not showing anything. Okay, zero point 0.5 millisecond, it means 2 kilohertz, right? 0.5 means 2. 0.5 means 1 upon 2, right? Sorry. Zero point 0.5 means 1 upon 2. So 2 kilohertz it is. So 2 kilohertz means exact frequency equal to 2 kilohertz. Okay, so I will put greater than or equal to 2. Let's say I'm putting 0.01. So it is 100 kilohertz. Then what will happen? Let's see. You will get so many samples. Let me increase the frequency. Yeah. You are getting too many samples in one cycle. It means you are converting your continuous signal into discrete. But again, in discrete also, you are putting, let's say, 200 samples in one cycle. It means again you are sending 200 values in your band limited transmission medium. So you are again overburdening your transmission medium. So it is again not good. So oversampling or undersampling is not good. Undersampling is not good because you are not getting proper signal at the receiver side, and oversampling is not good because you are sending again so many values into the transmission medium. But if you will do the proper sampling means it should be slightly greater than 2W, slightly greater than 2W. It means you can put it 3 kilohertz up to 10 kilohertz, it is okay, but you cannot put it 100 kilohertz, because of, if we are putting 100 kilohertz, it means you are again increasing number of samples too much. So there is no use of converting continuous into discrete. Okay, so depending upon the bandwidth you have to select this Nyquist rate. That is all about Nyquist rate or sampling theorem. If you understand this Nyquist rate, then I can show you one animation. This is not video, don't worry, this is not video. It's an animation by which you can understand what is happening. So see, Nyquist theorem, sampling theorem, or sometimes it is also known as Shannon theorem, because Shannon and Nyquist both have given this theorem. So see here, what I want to show through the animation. One signal frequency is there which you can increase and decrease according to your requirement, and one sampling frequency is there which you can increase or decrease. Right, now I want to see that if I will increase or decrease signal frequency, then how much sampling frequency will give you proper reconstruction at the receiver side. So let me set this sampling frequency to 10 kilohertz or 10 hertz, I don't know, 10 hertz is. So see, I have set the signal frequency to 10 hertz. Now sampling frequency. How much sampling frequency should be there so that you can reconstruct your original signal? At least twice. So it should be greater than or equal to 20. Now it is 20. So see, you can follow these samples and you can get the same shape of sine wave signal. If you will connect these all points, then you will get the shape of sine wave signal only. It means reconstruction is possible. Proper reconstruction can be done at the receiver side. Now, if you will decrease this, see, if you are decreasing the sampling frequency like this, I am putting signal frequency 10 and I am putting sampling frequency less than 20. Right? I am putting sampling frequency less than 20. Then what will happen? Now they are saying that if you will connect these points, red color points, then see they are showing this green color dotted line. But whenever at the receiver side, if you will join this red dots, then can you say that you will get the same shape, green color line? No, because you can join it with the straight line also. It means it will give you the triangular wave. See, straight line here, straight line here, so you will get almost like triangular wave. You will not get sine wave. It's not possible, I mean, right? So every time it will not be possible to reconstruct the original signal if you will keep your sampling frequency less than 20. And if you will increase the sampling frequency greater than 20, like let's say 30, 33, 34, right? Now what will happen, that if you are going to join your red color dots, then you will have so many points, right? So anyway, like after this, you are again going to here, and if you will make the plot by your own, you will get anyway the sine wave signal, but there are so many samples. There will be so many samples. If you will follow only in one direction, then you will get the sine wave. It is almost a sine wave, right? At here also and at here also. But the problem is there are so many samples, and you know don't need this many samples. So keep it as minimum as possible. And the other thing you have to take care is the signal should be reconstructed. If you will keep it exact 20, then see your samples are almost at this points, like your original signal and your sampling samples are almost in the same points, right? This sine wave 0 and this sample 0, this sine wave 0, sample 0. So you will get, right now the samples are not showing here, but there are also samples. So if you will join these all samples, you will get exact sine wave signal as you are transmitting in the transmitter side. So this type of animations are given in the internet for understanding that how your sampling frequency should be. Next, as I told you, that if you are keeping your sampling as less than twice of W, then it is known as undersampling, right? And why undersampling is not good? Because undersampling will create aliasing effect. So let me tell you what is aliasing effect. If you are keeping your sampling frequency exactly equal to twice of maximum frequency, then if you will plot your signal into the frequency domain, excess of W means frequency domain signal, then your signal, each signal will not be overlapped with the other. Your signal will be same as the input signal. But if you will keep your sampling frequency less than 2W, then what will happen? Your sampling signals in the frequency domain, your signals will be overlapped with the each other. And this overlap area, right? Overlap area, what this effect will occur, this effect is known as aliasing effect. Because of this overlapping, you will not able to retrieve the information correctly. Some of the information will mixed with the other signal. So you will not get proper signal at the output side, and that this effect is known as aliasing effect. I will tell you about aliasing effect in detail in next experiment. Right now, you just have to understand that if you will do under sampling, then in the frequency domain, you will get the overlapped signals. So whenever your signals will be overlapped, aliasing effect will occur. Okay, that we will study in the next experiment.
Ma'am,
Now, before going to
ma'am.
start, yes, just a minute. Yes, yes,
Hello, ma'am.
Arafat.
Yeah, ma'am. Ma'am, when we are sending any information, we are not sending one single sine wave, right? We are
Right,
sending
right,
one, two,
right,
three.
right,
So
correct.
In the Nyquist, they are saying then we have to take the highest frequency.
Right,
Okay. Then what is the proof that my highest frequency sine wave will take my information?
right.
It could be that another one also taking.
No, let me tell you, Arafat. I understood what you are facing confusion. where you are facing this confusion. I am saying that if you are taking, let's say, composite signal, one of let's say 1 kilohertz, second is of let's say 0.5 kilohertz, and third is of let's say 2 kilohertz. So what will be the Nyquist frequency? Just a minute. What will be the Nyquist rate for each signal? For 1 kilohertz, the Nyquist rate will be 2 kilohertz. For 0.5, it will be 1 kilohertz. And for 2 kilohertz, it will be 4 kilohertz. Now, what will happen that if you will keep 1 kilohertz, right, as your Nyquist rate, then this will be the undersampling for 2 and 4. That is for this two signal. If you will keep it 2, then it will be okay. If it is oversampling, it will not create a big problem if bandwidth is supporting, right? Your bandwidth is supporting, then it will not create a big problem. But for 4 kilohertz, it will be undersampling, so it is not advantageous. But if you will keep your Nyquist rate 4 kilohertz, then it will be oversampling for these two signals, but no undersampling for any signal. Undersampling will create much problem. Your signals will be overlapped with each other. Information will be mixed with the another, and you will not get the proper output at the receiver side. But yes, if you are keeping oversampling, then what will happen? Let me show you. This was also there in this PPT only, if you have observed or not. Yeah. If it is oversampling, then there will be gap between the signal. No problem. If there is a delay, right, if there is a delay between two samples coming, then it is okay, but the overlapping will not be tolerable, right? So overlapping is not allowed. So aliasing effect is the most critical thing. So you have to select the maximum frequency to calculate the Nyquist rate. Am I able to explain you, Arafat? Is it okay? That's what you want to ask? Yeah, okay, fine. Now, the next thing is we are going to make the multisim circuit for sampling and the reconstruction at output side. But before going to understand that, just watch this last video and then we will make the multisim circuit. That is the end of this today's session. But yeah, that will give you the big task. Okay, it was not that easy. But let us see this video.
Sampling, when a signal is digitized. The effect results in a false digitized signal with a frequency lower than that of the original analog signal. The frequency.
Yes? Are you able to listen the audio?
Gone again.
Yes, Arafat?
I'm checking out the screen.
The screen, I don't know why this screen is going every, just a minute. Okay, fine. Okay, are you able to see the screen now?
Yeah.
Are you able to see the screen, guys?
Yes, ma'am.
Okay, fine. So, see this video.
Aliasing is the effect of an insufficient sampling when a signal is digitized. The effect results in a false digitized signal with a frequency lower than that of the original analog signal. The frequency of the aliased signal can be anywhere from DC up to 1/2 of the sampling frequency. According to the Nyquist theorem, the sampling frequency must be at least twice the highest frequency contained in the signal to avoid aliasing. The Nyquist criterion guarantees that there are enough sample points to properly reconstruct the signal, provided the signal is a sine wave. Clearly, if the signal is composite and contains several frequency components, the sampling frequency must be at least twice the highest frequency component. An ideal square wave is an example of such a signal. It contains infinite frequencies, theoretically making it impossible to properly digitize. Aliasing could happen in movies, in a situation called wagon wheel effect. This is the effect when moving wheel seems to stand still or the propeller of an airplane appears slow. It could also happen in digital texts and pictures, causing them to look blurry. Aliasing happens in acoustic too. It translates to poor sound quality and static. An oscilloscope can be used to illustrate the effect of aliasing on a signal. Consider a 10 MHz sine wave. When the time base of the oscilloscope is properly set, the oscilloscope sampling rate is sufficiently high to prevent aliasing, and the signal appears normal. However, at bigger time scales, the oscilloscope sampling rate is lowered and the Nyquist criterion is no longer met. This causes aliasing, making the frequency and the shape of the signal dramatically different. A sampling frequency equal to the signal frequency results in a solid line. Notice that since the two frequencies cannot be made exactly the same, the line is not stable. To prevent oscilloscope aliasing, either an anti-aliasing filter must be used, or the oscilloscope must be able to sample the signal according to the Nyquist theorem.
No sound, man.
Okay, can you hear me now? Hello?
Yes.
Okay, fine. So by this video, actually, they have explained just the what is the effect of aliasing in the different applications, right? So they are saying that let's say you are simply doing transmission and reception of text, right? So even if you are sending a text or image, right, then what will happen? That image will look blurred because of aliasing effect, because at some points the two signal values will be mixed and you will look that blurred images there because two information are mixed together and you will not get the proper information at some points of that image, right? And even in the video, if you will see the video and at some points if you are seeing that let's say video is let's say whenever you are looking at the video and let's say one picture is going and the second picture is coming and both pictures are mixed together and you will see the another picture which is not a part of video, but whenever you are mixing two pictures in one video then you will look the different effect in that video. So this type of effects can come in the different type of data. It can come into the text, it can come into the picture, it can come to the video. So aliasing effect is not good for any transmission, any type of data transmission, right? So that's why the sampling theorem is very important. Now the last part of this experiment is we are going to conduct one transmitter circuit, sampling circuit at the transmitter side and the reconstruction circuit at the receiver side. So let me show you the circuit what I have already made previously. Okay, I have already made the circuit. This is the sampling circuit in which let me show you. Can you see the screen?
No.
Okay. Okay, now are you able to see the screen?
Yes.
Okay, fine. So see this much part of the circuit is the sampling, which we have already seen in this design, right? We have multiply sine wave signal with the pulse wave, and we got sampling in the output of CRO. Right. So this is the sampling circuit. The same sampling circuit is designed over here. But the other side, reception side, what will happen? How this original 1 volt 1000 hertz signal will be recovered, right? So for this, they have used one low pass filter, active low pass filter. right? In active low pass filter, as an active component, they have used operational amplifier. I hope you know this operational amplifier, right, everyone? You have studied this operational amplifier in BW. So let me tell you what is operational amplifier. Operational amplifier is actually the name itself says that amplifier which does the different mathematical operations. Amplifier which does the different mathematical operation. So which type of operation the op-amp can do? Let me tell you, operation can do addition, subtraction, multiplication, integration, differentiation, filtration. So many tasks this amplifier can do. So here also we have put one amplifier which is doing filtering. Which type of filtering? So see, if R is connected like this and C is connected with the ground. So which filter is this? This is. Do you know anything about filter, everyone? Low pass, high pass, and everything. Yeah, Arafat. No one can do anything if you hate the calculus. Anyway, do you know what is filter, everyone? Okay, so let me tell you what is filter. Filter, if you are saying low pass filter, what does it mean? The low frequencies can be passed by that filter. Only if you are saying high pass filter, so only high frequencies can pass. If you are saying band pass filter, so it means band of frequencies can pass. Whatever band you will select, that band only will be passed. The other frequencies cannot pass. So here we are going to use low pass filter in our circuit. See, this op-amp is positive. At the positive terminal, you are connecting output of sampling. It means this is non-inverting operational amplifier. Non-inverting terminal is connected with the output of sampling. That's why it is known as non-inverting amplifier. And inverting terminal is connected to ground. That's why it is known as non-inverting amplifier. So in the non-inverting amplifier, it amplifies. No doubt, it amplifies the signal with the gain of R3, 1 plus R3 upon R2. I don't know you remember these equations or not, but yes, this is the equation for non-inverting amplifier gain, that is 1 plus R3 upon R2. So your signal will be amplified by 10. 20 upon 10 means 10. 10 plus 1 is 11. 11. Right, so your output signal amplitude is 1 volt, then at the operational amplifier you will get 11 volt. Right, this is the amplifier. But what is this RC combination? This RC is, let me tell you in the paint. If you will say R into C, then that is equals to time constant. Sometimes in many books they are writing it as time constant. So time component will be given by R into C component. So if you will opposite it, that is, let's say you are saying 1 upon R into C. So what does it mean? It is F, that is frequency. Right, so which frequency can pass through this low pass filter, that you will decide by putting this R and C value. I have taken different values, and finally by this value I am getting the exact 1000 hertz frequency. So low pass filter, it means the low pass filter will work like this. So let's say this is your frequency axis. So low means starting from 0. So 0 to some frequencies only it will be passed, and for other frequencies output will be 0. So which is this frequency? That can be set as, this is known as cutoff frequency. So this cutoff frequency will be set by this equation 1 upon RC. Right, so I have taken the R and C value such that, so that I can get F equal to 1 kilohertz or 1000 hertz. So this is my capital F. Right, and which is 1000 hertz, what I have set by putting these values. Right, so this is the low pass filter which will pass only 1000 hertz frequency. If there is any noise greater than 1000 hertz will come, then it will be blocked by by this op-amp as low pass filter, and obviously whenever you are transmitting some signal, then attenuation will occur in the transmission medium, so amplifier is required at the output. So that's why we have put one amplifier also at the output frequency, at the output side. So just a minute, I have to stop it from here, and then only I can run the circuit. Now let us run the circuit, but okay, let me not show you the output. Let us see only input in the channel A. Right, for at the transmitter side, what we are transmitting, that is sampled signal. So let us see the sample signal. See, this type of sampling signal we are transmitting from the transmitter side. But receiver side, what I want? I want this type of sine wave, 1 volt signal, 1000 hertz frequency sine wave. So I want this type of signal at the output side. So are we getting the same after this amplifier? So we want to check it. So let's check. The B channel of the oscilloscope is connected with the output of this operational amplifier. And now let me select this wire color is green. Sorry. And let us run the circuit. And let me put this signal to the upper position, this signal to the position. So see, this is your sampled signal at the transmitter side, and this is your reconstructed signal at the receiver side. Now you will think that received signal is yet not proper, right? You can make it proper by increasing the sampling. I told you that I will explain you the reconstruction by taking many samples. So let me increase this frequency. So instead of 100 microsecond, let's say I am putting 10 microsecond, and let's see what is happening. Just a minute. For some time it will not be stable, but after some time it will give you some outputs. So see, even in the oversampling also, I am getting so much noise. So let me set this in the proper manner again. So instead of 10 microsecond, let's say I am setting it to 15 microsecond. And now let us see what is happening. So see, from the first case, we have set it to 100 microsecond. Right now I have set it to 50 microsecond. So see, the reconstruction is more smoother, right? Reconstruction is more smoother. If you will do sampling again, the problem will occur, but okay, we will keep it perfectly so that we can get more smooth signal. Now let me show you all three signals together. One signal is this one, second is this one, and third one is this. So let me connect another CRO for that purpose, because only two channels here, this CRO can only show you two waveforms. So let me put it 4 channel oscilloscope. 4 channel means 4 signals you can see together, in which negative is not required. You need not to connect to negative. So first I want to see is the input. Second I want to see is the output of multiplier. It will give me the sampling. And the third I want to see this is the output of operational amplifier. Now let me run the circuit. And just a minute, I have to set it according to my requirement. In channel A is the red color signal. Okay, so I am decreasing the voltage per division so that I can see the bigger signal, and I am setting it to the top. Now for channel B, you have to click over here, channel B, right? So channel B will come into picture. So in channel B also I want to decrease the volts per division, and let's say I am setting it to second position. And for channel C, I have amplified, that's why this big signal is there, right? I have amplified the signal, that's why this big signal I am able to see in the output. Right? So these are the 3 signals. First is the original signal, second is the sampled signal, and third is the your final reconstructed signal at the receiver side. Now at channel C, let me tell you, if you will put in the same voltage per division, that is 5 volt. For channel B also we have put it, okay, 1 volt per division. In channel A, 2 volt. Channel B also, let's say, put it to 2 volt per division. In channel C also, let us put it to 2 volt per division. Okay, we are getting so big signal. So for that, let me decrease this. Gain, I'm simply decreasing the gain of the amplifier. Value of this resistor. Let's say it is 10 ohms, so I will put it to 10 kilo ohms. You see, now I am getting very small signal, so let us again increase the gain. Let's say instead of 20, I am putting it to 50 or 100. For 10 times. I am putting the 10 times gain. Okay, now see, I'm not able to see the proper signal again because so much resistance is there. So you can set the values to check the different type of output. Huh? I'm just trying in every different batches, I'm trying the different values of R and C and everything, and I'm getting the different type of signal. So wherever you are getting a proper signal, you can finalize that one. That will be the goal of doing this. See, I am getting the reconstruction, but not proper. I am getting here many values, right? I'm not getting it smooth, right? Smoothness is not there in the output. So at whatever value you are getting the perfect value, perfect output, that should be the finalized by you. So according to your requirement, see, now we are getting much smoother value. Right, so this is the reconstruction of the input signal at the output side, and this is your sampled signal which you have set at the different sampling frequency. If you will change this sampling frequency, then also you will get the different type of reconstruction at the receiver side. See, the peak is not coming good. Okay, let me decrease this. See, peak is not good, right? You are not getting the peak values properly. So you have to change this value every time and you can check it. Yes, if you will keep one thing in mind that you have to follow the sampling theorem, then you will not get any mistake. For sure, you will not get much mistakes in the output side. Okay, see, you are getting the reconstruction, but some problems are there, right? So if you want to reduce this type of problem, you can increase or decrease the sampling frequency, and you can check. It is not smooth waveform, but if you will make it 50, as I have made previously, right? If you will make it 50 microsecond, you will get a proper smoothened signal at the output side. So by changing the different value of sampling period as well as by changing the value of gain and low pass filter, you can get the proper reconstruction at the output side as you want. Okay, so this type of proper reconstruction is possible if you will set the proper sampling period as well as proper gain and proper low pass filter characteristics. Is it clear, everyone, what we are doing in the sampling and why the sampling is required? Yes, I am taking the attendance, Matthews. There is a time. The lab is from 1:30 to 3:30, and right now it is only 3. Okay, lab is up to 3:30. So wait for some time. I will take the attendance by myself. Don't worry. Okay, so okay, I'm saying I hate this op-amp, and op-amp can do calculus operations also. Yeah, Rafat, but if you will study operational amplifier in detail, it is very good. Arafat, operational amplifier is very good to study. If you will study it in detail, it is interesting, very interesting. Why you hate this type of operational amplifier? Let me tell you, because you have studied very little bit about them, and little bit knowledge is always dangerous. Either you have to study it completely, or don't study anything. And in your syllabus, like something is there that we cannot explain you in deep, right? And that's why you are facing such type of problem in many subjects. I understand. Okay, Matthews. Okay, so it is for your safety that if you lose the connection, then your number is with me. Yeah, okay, no problem. Okay, anyone is having any doubt in multi-sim socket? Okay, so if you don't have any doubt, then your task for this experiment is you have to make this circuit in your by your own in your multisim, right? And if you are facing any problem, if you feel any confusion, then you can come with your doubt in the next lab. Okay, this is the task. Only you need not to submit anything. Don't worry. You need not to submit anything. You just have to draw this circuit into the multisim and see the output waveforms. That's it. Okay. So no homework from my side.
Ma'am,
Yes.
to see the perfect signal in
Yeah.
output,
Yeah.
is there any question? Is there like we are getting gain and low plus filter value as our requirement? What
Yeah.
we are seeing the oscilloscope.
See, whenever
So
you
to
want,
get the perfect one.
yeah, Rafat, you if you want to get the perfect waveform at the output side, see, whenever someone is designing the circuit, they are keeping so many things in mind. They like whenever they are designing a, let's say, output low pass filter, whenever they are designing output low pass filter, they are keeping some things in mind. Hello.
Yes.
Yes, ma'am.
Okay, sorry, my laptop was discharged completely. That's why I have connected through the phone. See, what I want to say, Arafat, is whenever someone is designing any circuit at the receiver side, they are taking so many examples and they are trying so many things on that. And after confirming that this will be good for almost every type of signal, then they are confirming. So that's what I was doing in the sampling circuit. I'm taking so different type of examples, and I was showing you that how the designer will do the work. Right? It is not like the every theorem is, see, sampling theorem is only for deciding sampling period. Right? For low pass filter, what should be the gain at the output side? See, amplifier is not required in every case. Let's say in some of the transmission medium there is no attenuation, so no amplifier is required, right? So depending on the type of transmission medium and depending on the type of transmission of the data, the receiver circuit, the receiver filters are being designed. So they are designing by doing trial and error, because they even don't know that in this type of transmission medium what should be the attenuation. So they will first try on some of the data and then they will put it into the market, right? So this way the communication market will work. Is it okay, Arafat? Arafat? Okay. Fine. So anyone is having any doubt in multisim? So see, for today, there is no homework from my side, but everyone, I hope everyone will try this circuit by their own by putting the different values of low pass filter and gain and sampling period. I will provide you this multisim circuit into the canvas. So you can download this multisim socket and you can check with the different parameters, right? I will put the same circuit what I have designed into the canvas, so that you can directly open it from canvas, right? So it will open in the multisim only. So this file I will upload in canvas. You have to try it by your own till next lab, and then in next lab if you are facing any problem, then you can raise your query. Is it okay, everyone? Clear? If any doubt, then you can tell me for today. Yeah, I will share the PPT also. Sure. I will share this PPT as well as the multisim socket today. Okay, fine. So, depending on today's learning, sampling theorem, let me ask you few questions, right? And then we will end up the session. So, my first question is for David. David, can you hear me? David? Yeah, I will share the PPT. David, first question for you. And the question is, can you tell everyone that what is sampling? In your words, what is sampling? I want answer from David. Hello, David. Okay, I think he's not in the position. Okay, there is a. No one is answering. Why? Gloria?
Yes, ma'am. Yes.
Yes, there is a. Okay, so the question is, what is sampling?
I'm not sure, but I think it is a frequency that is transmitted through the medium.
Sorry, can you repeat it?
I think it is a frequency that passes through the medium, the sampling frequency, I think.
Frequency. No, I am saying that what is this process? What do you mean by sampling process? What do you do in the sampling?
Hello, ma'am.
Yes.
It is random selection of the wave.
Yes. Converting. You can write it. If you are not able to speak properly, you can write it into chat box.
I think, ma'am, it is the reduction of continuous time to discrete time. The reduction of.
Yeah, yes. If you are converting continuous signal into the discrete signal, it means you are taking only some points of the continuous signal, and at the receiver side, by those points only, you are predicting about the original signal, that how your original signal will be, right? So that is known as the sampling process. Okay. So my second question is for Krishna. Krishna?
Yes, ma'am.
Okay, so for the second question, I want to ask that if I will
No, ma'am.
increase
No, ma'am. Not now, ma'am.
no, I'm asking, you have to answer. See, my question is, if I am increasing my sampling frequency, increasing and increasing, so does it generate any sampling error? I repeat my question.
Yes, ma'am.
The sampling theorem says that my sampling frequency must be greater than or equal to 2W, right? So
Yes, ma'am.
if I am increasing it even greater than 2W, then sampling error will be increased or not?
Ma'am, I think not.
Not. Yeah, obviously. We can keep it greater, but we cannot keep it less. Yeah, we
Yes,
can
ma'am.
keep greater or equal, but not less.
Not
Okay,
less,
fine.
yeah.
Yeah, okay, fine. And last question for why others have been left. Okay, fine. Last question. Where is Shekhar? Yeah, Shekhar.
Yes, ma'am. I am.
Yeah, okay, fine. So last question for you. Can you
No, ma'am.
tell
I have.
me? Hello.
Yeah, ma'am.
Yeah. Can you tell me if the signal frequency is 10 kilohertz? I repeat, if the signal frequency what you are transmitting is 10 kilohertz, then what should be the minimum sampling frequency you should set so that you can reconstruct the signal properly?
No.
What should be the minimum sampling frequency you should set if signal frequency is 10 kilohertz?
Mom is lying.
5 kilohertz, ma'am. 5 means 0.
What? Shekhar, I'm not able to hear you.
No, I don't know, ma'am.
Why you don't know? It is the sampling theorem. It is Nyquist rate. If signal frequency is 10 kilohertz, what should be the sampling frequency? It's a Nyquist rate. I have already said this equation in the previous question.
10 divided by 5.
Why
0.
divided by 5? Why divided by 5?
Ma'am, I
Arafat?
just assume, ma'am.
Arafat?
Yes, ma'am. Yes, ma'am. It will be 20 for the
20,
minimum.
right? It should be twice of. It should be minimum twice of the signal frequency. So 2 into 10 kilohertz, that is 20 kilohertz should be the frequency. Okay, it should be the minimum frequency. Okay, so everyone kindly remember these 3 or 4 things. These are the important for the sampling theorem. If you have any doubt, then you can ask me in the chat box. Otherwise, you can write your enrollment number and leave the meeting. That's all for today. Yeah, you are very speedy in writing the number, huh?
Ma'am,
Yes.
when you have uploaded the worksheet 1 in the canvas, I'm talking about the first
Yes.
one. There is some errors are there. Like I got another one. I see another one worksheet. I think you have uploaded or you have updated. I don't know. But the first one I downloaded, it was having something like not the sequential manner. Like until question 4 is there, and again it started from ABC. So I submitted that format.
See, actually, let me tell you, Arafat. Actually, we 4 or 5 faculties are taking the subject in the different class. So I have to check that who has updated. So I don't know if anyone has updated that worksheet file or not. So I will look into that and I will tell you.
Not the
Otherwise, it
updated,
will
not
be
the
okay.
updated. Like the second one is having the sequential manner, like question 1, question 2, question 3, question 4, like that.
Okay.
But
Okay.
I have the one I have done. It was not having such a like, but I have
No
completed that.
problem.
That's
No
why I'm
problem.
wondering.
No problem. You have whatever you have done. You just submit that because I know which worksheet you have done. I know about that. So don't worry.
Yeah, I have done already. And I have uploaded already.
Okay. Then done. Okay. So anyone is pending for attendance?
Yes, ma'am.
What's your number?
193.
193. Okay. Okay, Nahum. Okay. Nahum, I have noted it. Yeah, Gloria, I got your number, 198. Matthews, I have already noted your number in very first, right? Because you have given it to me. Yeah, okay. I noted every number. Let me tell you if you have any doubt. 176, 172, 201, 188, 180, 191, 192, 193, 175, 183, 172, 190, and 198. Anyone pending?
Yes, ma'am. 193.
Yeah, it is already done. I have already told you 193.
Okay.
Thank you, ma'am.
Okay. So enjoy your day. Have a nice
Okay. Okay, good day.
There is no enjoyment, ma'am,
day. Yeah. Why?
because they have cut it our weekend. Right now, only one day weekend, only Sunday.
So sad. Oh, so sad. But in the weekend, we are also teaching you, right? So it is okay.
Ma'am,
Yeah.
you're working in the home right now or in the college?
Actually, right now we are working from home only. But within a week, if any work is there, then only we are going to the college. Otherwise, we all are working from home.
And the college is planning to open from August, like the 15th August. You told me something about like that.
Sorry. Can you repeat your question?
Like in this class, you have told us there is a plan of college that it will start from 15 August, like as a normal classes.
Actually, from 15th August, the government will give us the date that when we can open the college. It's not like that.
Okay,
15th from 15th August the college will open. Yeah, but from 15th August you will come to know that when your college will be open.
Okay. Thank you, ma'am. See you.
Okay. See you. Bye, everyone.